So now I'm going to talk about the negative multiplication property of inequalities and see if we can figure out what went wrong in Steve's example. Let's start by comparing some numbers. So compare each pair of numbers using an appropriate inequality sign. Obviously 4 is less than 8. 4 lies to the left of 8. But what happens if I multiply both the number 4 and the number 8 by negative 1/2? Negative 1/2 times 4 is negative 2. Negative 1/2 times 8 is negative 4. Negative 2 is greater than negative 4. So negative 1/2 times 4 is greater than negative 1/2 times 8. Notice that the sense of the inequality reversed when I multiplied both 4 and negative 8 by negative 1/2. Let's compare another pair of numbers. 6 is greater than negative 3. What happens when I multiply both of these numbers by negative 4? Negative 4 times 6 is negative 24. Negative 4 times negative 3 is 12. Negative 24 is less than 12. So negative 4 times 6 is less than negative 4 times negative 3. Once again, when I multiplied both of the numbers in the original inequality by negative 4, the sense of the inequality changed. Let's compare one more pair of numbers. Negative 10 is less than negative 5. What happens when I multiply both of these numbers by negative 6? Negative 6 times negative 10 is 60. Negative 6 times negative 5 is 30. 60 is greater than 30. So negative 6 times negative 10 is greater than negative 6 times negative 5. And one more time, when I multiplied both of the numbers in the original inequality by negative 6, the sense of the inequality reversed. Now I want to look at a little proof similar to the proof Steve looked at when he was multiplying an inequality by a positive number. So I'm going to start out with a more generic inequality. Suppose A is greater than B. Then I'm going to add negative b to both sides of the inequality using the addition property of inequalities. When I simplify this, I get a minus b is greater than 0. We can say this in words as a minus b is a positive number. If we take a positive number and multiply it by a negative number, we get a negative number. So if I take a minus b and multiply it by negative 2, I get a negative number. In symbols, negative 2 times the quantity a minus b is less than 0. That's the same as saying negative 2 times the quantity a minus b is negative. Well, now let's simplify this inequality. So if I distribute the 2, I get negative 2a plus 2b is less than 0. And now let's move that 2b to the right-hand side of the inequality. So I subtract 2b from both sides of the inequality. And when I simplify this, I have negative 2a is less than negative 2b. Let's compare to what we started with. We started with a is greater than b. We ended with negative 2a is less than negative 2b. Once again, we saw that when we multiplied both sides of an inequality by a negative number, negative 2 in this case, the sense of the inequality reversed. Multiplying both sides of an inequality by a negative number, in general, reverses the sense of the inequality. This is the negative multiplication property of inequalities. This is something you need to remember. So I'm going to give you several choices of ways you can remember this. The first one is multiplying both sides of an inequality by the same negative number does not change the solution set to the inequality if and only if you simultaneously reverse the sense of the inequality. Another way we can say that is multiplying both sides of an inequality by the same negative number results in an equivalent inequality if and only if you simultaneously change the direction of the inequality symbol. Yet another way you might remember that, multiplying both sides of an inequality by the same negative number reverses the sense of the inequality. That is, multiplying both sides of an inequality by the same negative number changes the direction of the inequality sign. So here's at least 4 different ways that you can remember this. I like to remember that multiplying both sides of an inequality by the same negative number reverses the sense of the inequality. This is the easiest way for me to remember it. you need to think about these different ways and decide which one is easiest for you to remember. The other thing you need to remember is the positive multiplication property of inequalities. Multiplying both sides of an inequality by the same positive number results in an equivalent inequality if and only if you retain the original direction of the inequality sign. So that's something you need to be careful with. There's a difference in inequalities between multiplying both sides by a negative number and multiplying both sides by a positive number. The surprise comes when we multiply both sides of the inequality by a negative number. So let's go back to Steve's example and see what went wrong. I actually want to look at this in two different ways. So I'm going to solve the inequality negative 3x is greater than 9 first by using this new negative property of inequalities, negative multiplication property of inequalities. So I'm going to divide both sides of this inequality by negative 3, which is the same as multiplying both sides of the inequality by negative 1/3. So I just talked about the negative multiplication property of inequality. This is when little bells start going off in my head saying, okay, I'm multiplying or dividing both sides of an inequality by a negative number. I need to reverse the sense of the inequality. So my greater than symbol becomes a less than symbol. So x is less than negative 3. Well, I said we could do this in two different ways. Even if we didn't have this negative multiplication property for inequalities, I could still solve this inequality. Takes a few more steps, but what I could do is move my variable term to the right-hand side and my constant term to the left-hand side. So I'm going to start by moving my variable term to the right-hand side by adding 3x to both sides of this inequality. That gives me 0 is greater than 9 plus 3x. And then I'm going to move my constant term to the left-hand side by subtracting 9 from both sides. That gives me negative 9 is greater than, and I have an error. This should be positive 3x. So negative 9 is greater than 3x when I simplify. Now the coefficient of x is a positive number. So if I divide both sides of this inequality by positive 3, the positive multiplication property of inequality says we need to retain the sense of the inequality. So my greater than symbol stays a greater than symbol. And when I simplify, I have negative 3 is greater than x. This is equivalent to the inequality x is less than negative 3. Well, let's go ahead and graph the solutions to the inequality x is less than negative 3. So I start with a number line. I need my variable x. And I can see that my endpoint is going to be negative 3. Negative 3 is not included, so I need to draw an open circle at negative 3. X is less than negative 3 means x lies to the left of negative 3. So I need to draw a line to the left of negative 3. And an arrow indicating that these numbers go on to the left indefinitely. Well, now I want to check my proposed solution. First, I'm going to check for equality at the endpoint of my solution set. So my endpoint is x equals negative 3. And if x equals negative 3, then negative 3x is negative 3 times negative 3, which is positive 9. Since I have 9 on the right-hand side of the inequality, I do have equality at the endpoint of my solution set. Now I need to check for the proper sense of the inequality at an interior point in my solution set. So let's pick an interior point, say negative 5. So if x is negative 5, then negative 3x is going to equal negative 3 times negative 5. And that's 15. Now I need to check that my inequality is correct. I need to know how 15 and 9 compare. Well, 15 is greater than 9, and that's the correct sense of the inequality. So my solution set checks. So now I need to go ahead and write out my solution. I'm going to write the solution in set builder notation. The solution set is the set of all x such that x is less than -3. I could have also written my solution set in interval notation. I think I'll do that on my next example. So in my next examples, I'm going to put everything together. Next, I want to solve 7 minus 4y is less than 12. The first thing I'm going to do is get my constant terms together on the right-hand side of the inequality. I do that by subtracting 7 from both sides of the inequality. When I simplify this, I have -4y is less than 5. To isolate y, I need to divide both sides of this inequality by -4. And I'm hoping at this point, little warning bells are going off in your head saying, hey, she's dividing both sides of this inequality by a negative number. I need to reverse the sense of the inequality. So this less than needs to become a greater than. When I simplify, I now have y is greater than -5/4. Now I could have also solved this inequality by isolating the variable term on the right-hand side. And notice in blue here, where I've isolated 4y on the right-hand side of the inequality. Then if that were the case, I would be dividing both sides of the inequality by +4. Dividing both sides of an inequality by a positive number retains the sense of the inequality. And if I did that, I would end up with -5/4 is less than y. That's equivalent to what I got, which was y is greater than -5/4. So let's go ahead and graph the solution set for this inequality. So I start with a number line and my variable y. My endpoint of the solution set is -5/4. I need to locate -5/4 on my number line. -5/4 is the same as -1 1/4 or -1.25. So I locate that point on my number line. Y is strictly greater than -5/4, so I need an open circle at my endpoint. And then I need an arrow, well, I'm going to draw a line first, to the right of -5/4, and an arrow indicating that these solutions go on and on and on forever. Well, let's check my solution set now. First, I'm going to check for equality at the endpoint of my solution set. My endpoint being y equals -5/4. And if y equals -5/4, then 7 minus 4y would be 7 minus 4 times -5/4. And that's 7 plus negative times negative is positive. 4 goes into 4 one time. 1 times 5 is 5. 7 plus 5 is 12. Exactly what I wanted. The right-hand side of the inequality is 12. So I have equality at the endpoint. Now I need to check for the proper sense of inequality at an interior point in my solution set. So I think the easiest test point for me is going to be y equals 0. If y equals 0, then 7 minus 4y is 7 minus 4 times 0. 4 times 0 is 0. 7 minus 0 is 7. And now I need to compare 7 on the left with 12 on the right. 7 is less than 12, so the sense of my inequality is correct. So it looks like my solution set checks. So now I can go ahead and write my solution set. The solution set is, and I'm going to write this one in interval notation, left-hand endpoint is -5/4, not included, so I use parentheses. There is no largest number. I indicate that with an infinity on the right-hand side, and infinity always takes parentheses. Now I could have written my solution set in set builder notation. The directions don't tell me which way to write the solution. It's a good idea for you guys to practice both interval notation and set builder notation, so you get used to both. Let's solve another inequality. 5 plus 2 times the quantity 3 minus t is less than or equal to 4t plus 11. First, I'm going to simplify the left-hand side by distributing the 2. So 5 plus 2 times 3 is 6 minus 2t is less than or equal to 4t plus 11. I can still simplify the left-hand side. I can combine the constants 5 and 6. That gives me 11 minus 2t is less than or equal to 4t plus 11. So I think I'm going to isolate my variables on the left-hand side and my constants on the right-hand side. I'm going to start by subtracting 11 from both sides of this inequality. This simplifies to negative 2t is less than or equal to 4t. Now, remember I said I was going to isolate my variable terms on the left-hand side. So to do that, I'm going to subtract 4t from both sides of this inequality. So now I have negative 6t is less than or equal to 0. To isolate t, I need to divide both sides of the inequality by negative 6. Are little warning bells going off in your head? I hope so. We're dividing both sides of an inequality by a negative number. We need to reverse the sense of the inequality. So the less than or equal to symbol becomes a greater than or equal to symbol. And simplifying, t is greater than or equal to 0, because 0 divided by negative 6 is 0. Now, if I had solved this same inequality by isolating the variable terms on the right-hand side, I would have ended up with positive 6t on the right-hand side, a coefficient of t that's positive. And dividing both sides of an inequality by a positive number retains the sense of the inequality. What I would have ended up with is 0 is less than or equal to t. But this is equivalent to what I did end up with, which is t is greater than or equal to 0. Let's go ahead and graph the solution set for t is greater than or equal to 0. So I start with a number line. This time it's a t number line. My endpoint is 0. T is greater than or equal to 0, so the endpoint is included. I need a solid circle at 0. T is greater than or equal to 0 means t is 0 or t lies to the right of 0. So I'm going to draw a line to the right of 0 and an arrow at the end indicating these solutions go on forever. Now I want to check my proposed solution set. I'm going to start by checking for equality at the endpoint of my solution set, my endpoint being t equals 0. So if t equals 0, then the expression on the left, 5 plus 2 times the quantity 3 minus t, would be 5 plus 2 times the quantity 3 minus 0. 3 minus 0 is 3, 2 times 3 is 6, 5 plus 6 is 11. Well, what about the right-hand side? That also involves a variable. So if t equals 0, then the right-hand side, 4t plus 11, would equal 4 times 0 plus 11. 4 times 0 is 0, 0 plus 11 is 11. And indeed, I do get equality at the endpoint. Now I want to check for the proper sense of inequality at an interior point in my solution set. This time, I think I'm going to use t equals 1 as my test point. So if t equals 1, then my variable expression on the left-hand side, 5 plus 2 times the quantity 3 minus t, would evaluate to 5 plus 2 times the quantity 3 minus 1. That's 5 plus 2 times 2, which is 5 plus 4, which is 9. And my variable expression on the right-hand side, 4t plus 11, would evaluate to 4 times 1 plus 11. 4 times 1 is 4, plus 11 is 15. Now I need to compare 9 on the left, 15 on the right. Well, 9 is less than 15, so my sense of my inequality is okay. 9 is definitely less than or equal to 15 because 9 is less than 15. Well, now I need to state my solution set. I'm going to state my solution set in interval notation. So I see my left-hand endpoint is 0. This time my endpoint is included. I indicate that with a square bracket. There is no right-hand endpoint. Again, I indicate that with infinity, and infinity always takes parentheses. So the solution set is 0 included to infinity. Now let's solve one more inequality. 3 plus 5y is less than 13. To solve this inequality, I'm going to move my constants to the right-hand side. I'm going to subtract 3 from both sides of this inequality. This simplifies to 5y is less than 10. Dividing both sides of this inequality by 5 being a positive number, I need to retain the sense of the inequality. When we divide both sides of an inequality by a positive number, which is equivalent to multiplying both sides of the inequality by the reciprocal of that number, we retain the sense of the inequality. So my less than symbol stays as a less than symbol. And this simplifies to y is less than 2. Let's graph the solution set for y is less than 2. So I start with a number line. It's a y number line. My endpoint is 2. 2 is not included, so I draw an open circle at 2. Y is less than 2 means y lies to the left of 2. So I draw a line to the left of 2, and an arrow at the end indicating these solutions go on forever. Now I need to test my proposed solution set. First, I'm going to check for equality at the end point of my solution set, 2 being the end point of my solution set. So if y equals 2, then 3 plus 5y would equal 3 plus 5 times 2. 5 times 2 is 10. 3 plus 10 is 13. The right-hand side of my inequality is 13, so I do get equality at the endpoint. Now I need to check for the proper sense of the inequality at an interior point in my solution set. I have 0 as an interior point in my solution set again, so I'm going to pick y equals 0 as my easy test point. So if y equals 0, then my variable expression 3 plus 5y would be 3 plus 5 times 0. 5 times 0 is 0. Add that to 3. I get 3. Now I need to compare 3 on the left with the 13 on the right. 3 is less than 13, so the sense of my inequality is correct. So it looks like I have the correct solution set. So now I need to write my solution set. So my solution set is, and once again I'm going to practice interval notation. This time there is no left-hand endpoint to my solution set. We indicate that with negative infinity, which always takes parentheses. My right-hand endpoint is 2, and 2 is not included, so I use parentheses to indicate that 2 is not included. Well, now I want to look at an example and see if you can spot the error. We're trying to solve the inequality negative 10 is greater than negative 5x. So all we need to do here is isolate x. To isolate x, I would need to divide both sides of the inequality by negative 5. That looks okay, except warning bells should always go off in your head when you multiply or divide both sides of an inequality by a negative number. When we do that, we need to make sure we reverse the sense of the inequality. That doesn't look like that happened here. Negative 10 divided by negative 5 is positive 2. Negative 5x divided by negative 5 is x. And this says 2 is greater than x. The correct solution should be 2 is less than x. So the error is right in the middle here. The sense of the inequality needed to change. What was written here was equivalent to the inequality 2 is greater than x. But a correct equivalent inequality is actually 2 is less than x. The sense of the inequality needs to be changed when dividing both sides of an inequality by a negative number. Let's look for the error in this example. We have the inequality 3x minus 9 is greater than 6. To solve this inequality, we could isolate the constant terms on the right-hand side. To do that, we could add 9 to both sides of this inequality. So here I see 9 being added to both sides of this equation. Wait a minute, we had an inequality. So I see an error already. This greater than symbol became an equals sign. And I see equal signs all the way down. At the very end, I see x is greater than 5. X is greater than 5 actually is an equivalent inequality to 3x minus 9 is greater than 6. If we insert greater than symbols all the way through here, this solution process would be correct. The thing that you want to note, though, is if instead of isolating 3x on the right-hand side, which caused us to have to divide both sides of the inequality by positive 3, which retains the sense of the inequality, if instead we had isolated the variable term 3x on the left-hand side, or excuse me, the right-hand side, then we would have had to divide both sides of the inequality by a negative number, which reverses the sense of the inequality. So if we haphazardly go through and try to solve an inequality as if it's an equation, we always run into the possibility that we're not keeping track of what's happening to the inequality. And if we had come to a point where we had to multiply or divide both sides of the inequality by a negative number, we wouldn't have reversed the sense of the inequality, and we would not have come up with a correct equivalent inequality at the end. Now I want to turn over to Anne, who's going to talk about some applications.
In this part of the lesson, we're going to start looking at applications of linear equations and inequalities. This is just an introduction. We'll be discussing this topic over the next several lessons. To start, we're going to look at a couple of introductory examples, which are extensions of problems we've done before. And then we're going to look at one application leading to a linear equation. And after we've worked through this, we're going to look at some problem-solving steps that we used to solve the problem. And finally, we're going to look at an application leading to a linear inequality. So let's start with some introductory examples. Anne's total cost, C, measured in dollars, for printing catchy slogans on N water bottles is given by the formula C equals 300 plus 0.25 N. The first production run printed bottles for the Portland Marathon. Anne's total costs were $987.50. How many bottles were printed with the slogan? So the first thing we want to ask is, what do we know? Well, in this problem, we're given a formula for the total cost. We're also told that the total cost for this particular production run was $987.50. What we don't know is the number of bottles that were printed with the slogan, but I can use the formula to help me determine this. So I know that the costs are $987.50, and I can replace the letter C with the expression that represents the total cost. And now I have a linear equation which I can solve for N to answer the question. So let's solve this equation. The first thing I want to do is isolate the term that has the n in it. So I'm going to start by subtracting 300 from both sides of the equation. So I'm left with 0.25n on the left and $687.50 on the right. So now I can divide both sides of the equation by 0.25. And then figure out an equivalent equation, n equals a constant. But here I probably want to pull out my calculator to do the computation. So $687.50 divided by 0.25. That equals 2,750. So now I want to check my solution. So if n equals 2,750, I want to evaluate the total cost for that number of water bottles. Then 300 plus 0.25n equals 300 plus 0.25 times the number of bottles we just determined, 2,750. And again, I'm going to pull out my calculator to do this check. So I have 300 plus 0.25 times 2,750, and there's my $987.50. So my solution checks. And now I can answer the question, how many water bottles were printed with the slogan? And printed the slogan on 2,750 water bottles. So let's look at another example. This is related to the one we were just looking at. But now Anne has only $2,000 of capital to invest in her water bottle enterprise. We have the same formula for total cost. But now the question is, how many water bottles can be printed with the slogan if Anne's total costs must be at or below $2,000? So when we're trying to understand the problem here, we realize that there's a maximum cost that Anne can afford. So we want to keep our costs below this $2,000. This suggests an inequality. So what do we know? Same formula for total cost. And we also know the maximum total cost has to be $2,000. So a way I can write this in terms of my formula is the cost must be at or below $2,000. And if I replace C with the expression that calculates the total cost, I end up with a linear inequality, which I can solve. So let's solve this. So I'm going to start by isolating the variable term, subtracting 300 from both sides of the equation, inequality, excuse me. So I have 0.25n is less than or equal to 1,700. And this time, rather than pulling out my calculator, I'm going to write 0.25n as n over 4 and multiply both sides of the inequality by 4. Now I've multiplied both sides by a positive number, so the sense of the inequality remains the same. So 4 times n over 4 is just n, which is what I want, and 4 times 17 is 68, so I have n is less than or equal to 6,800. So now I want to check my solution, and I have a graph of the solution set here. 6,800 is here on the n number line, and my proposed solution is n less than or equal to 6,800. So I'm going to start by checking for equality at the endpoint of the solution set. So if n equals 6,800, in this situation this means if 6,800 bottles are printed with the slogan, then the total cost can be calculated by 300 plus 0.25 times 6,800. And here I think I will pull out my calculator to do the calculation. So 300 plus 0.25 times 6,800, that's 2,000. So when I print the slogan on 6,800 water bottles, I have exactly costs of $2,000. I didn't want to exceed those costs, so everything is okay. Now the next step for doing a check is I want to check for the proper sense of the inequality at an interior point in the solution set. So I'm going to choose an interior point in the solution set to work with. And I think I'm going to choose n equals 1,000. So if n equals 1,000, then my total cost expression becomes 300 plus 0.25 times 1,000, and multiplying 0.25 by 1,000 just moves the decimal point 3 places to the left, or to the right, so that's 250. So my total cost will be $550. And $550 is less than or equal to 2,000, so everything's okay in the interior of the solution set. So now I can answer the question. How many water bottles can be printed with the slogan if n's total cost must be at or below $2,000? Well, we saw 1,000 water bottles will work, and we also saw that 6,800 water bottles will work. As long as the number of water bottles don't exceed 6,800, Ann's cost will be below $2,000. So Ann can print the slogan on, at most, 6,800 water bottles. So now we want to look at an application leading to a linear equation. So here's the problem. Anton is running on a treadmill that tells him that he has burned 750 calories, but the treadmill will not display the distance he has run. Anton knows he burns 100 calories per mile. How far has he run? Now in this problem, we don't have a formula to work with like we did in the last two examples. So our task over the next few lessons is going to be to come up with an equation or perhaps an inequality that will model the problem and allow us to answer the question. Now in this particular problem, you can kind of think about it and figure out how far Anton has run, but what we want to look at is the steps we would use in order to write an equation which we could solve to answer the question. So the first thing we want to do is to try to understand the problem. And for this example, what I'm going to do is just do some calculations and keep track of them in a table. So I have a table here, and I'm going to label the first row with the distance run in miles. So this is how far Anton has run on the treadmill. And in the second row, I'm going to calculate the total calories burned. So if Anton has run 0 miles, he will burn absolutely no calories from running. If Anton runs 1 mile, he's burning 100 calories per mile, so he will burn 100 calories after running 1 mile. If he runs 2 miles at 100 calories per mile, he'll burn 200 calories. If he runs 3 miles, he'll burn 300 calories. So we can see that it's very easy to calculate the total calories burned. We take the distance Anton has run and we multiply it by 100 calories per mile. So I've summarized this information that we need from the problem to answer the question, how far has Anton run? So what I want to do first is to define a variable to represent the unknown quantity. The unknown in this case is the distance Anton's been running on his treadmill. So I'm going to let D represent the distance, and I'm going to note that we're measuring distance in miles. Anton has run on the treadmill. This is the unknown. Now I'd like to write an equation to model the problem. Well, we can think about what we did in our table. We took the distance Anton ran, and we multiply that by 100 calories per mile, and that equals the total number of calories burned. So now I have a very simple equation I can use to solve this problem. So let's solve the equation and then go back and check it, but this time check it in the context of the problem. So I have 100D equals 750, certainly one of the easiest equations we've seen for a while. So I'm going to divide both sides of the equation by 100 to isolate D, and I have D equals 7.5. Now I want to check the solution. D equals 7.5 is telling me Anton ran 7.5 miles on the treadmill. So I want to do a check. If Anton ran 7.5 miles, then he burned, and let's do the calculation. We take 100 calories per mile, and we multiply it by 7.5 miles. Notice the units cancel here. Miles over miles simplifies to 1. And we have 100 times 7.5 is 750 calories. So our solution makes sense in the context of the problem. Now we're going to look at this another way. What I have here is a graph that shows us the total calories that Anton has burned after running a certain distance. On the horizontal axis, I have the variable D representing distance, and the scale is 1. So here's 1 mile, 2 miles, 3 miles, etc. And on the vertical axis, my variable C for calories burned, and the scale is 100. So I have 100 calories burned, 200 calories burned, etc. And if we look at the table we made while we were thinking about the problem earlier, we see we have values in our table which correspond to ordered pairs on the graph. So here's the point 0, 0. Anton runs no miles, he burns no calories from running. Here's the point 2, 200 from the third row in our table. If Anton runs 2 miles, he's burned 200 calories. So let's think about how we can use this graph to check our solution. We were told that the treadmill informed Anton he had burned 750 calories. We want to know how far he ran. Well, if I look at the ordered pair on the line that represents this relationship, the second coordinate of this ordered pair is 750. If I read down to the horizontal axis, I can see that the number 7.5 looks like it should be the first coordinate, which is the distance Anton ran. So the graph confirms our solution. So I feel pretty good about the work I've done. So now I want to go back to the problem and answer the question. The question was, how far has Anton run? Anton ran 7.5 miles on the treadmill. So we've just spent a lot of time solving a particular problem. And now I'd like to talk about some problem-solving steps that we used. The first thing we did is we tried to understand the problem. We read the problem carefully. And when you're reading a problem, you can ask yourself questions like, are there any words or concepts that need to be researched? Sometimes you'll have to look up a formula from geometry or perhaps some other area. You might want to ask yourself, have I solved a similar problem before? When we just start off problem solving, we won't have a lot of different types of problems to draw upon. But as we do more and more problems, you'll see that many of them are similar to one another, even though on the surface they may appear different. Can I solve a simpler problem? This is a technique you'll see us use several times over the next few lessons. What is the unknown? We always have to make sure we know what it is we're being asked to find. And we also need to know what information is given. What information is given in the problem which will help us determine the unknown. Sometimes we might want to determine a verbal model of the problem situation using a table if necessary. We did this with Anton. We decided that in order to calculate the total number of calories he'd burn, that we multiply 100 calories per mile times the distance he has run to get that calculation. That's a verbal model. The next step, once we understand the problem, is we're able to clearly define a variable to represent the unknown quantity. So a clearly defined variable states explicitly what the variable represents. We really don't want any ambiguity. A clearly defined variable includes the appropriate unit of measurement. So as we work through some examples over the next few lessons, we'll see that units do matter. So here's an example of a clearly defined variable. Let D represent the distance in miles Anton has run. We know exactly what D is. We also are including units in the variable definition. Here's kind of a lousy variable definition. D equals distance. There's just not enough information here for somebody else to go back and try to understand your problem solution. Now we want to write an equation to model the problem. And this step is a lot easier if you've completed steps 1 and 2. The more time you take to try to understand the problem and the care you take in defining your variable makes writing the equation kind of easy, but only after you've done a thorough job on steps 1 and 2. Then we solve the equation and check the solution in the context of the problem. We did that in the equation that we solved for Anton's dilemma on the treadmill. Also, when checking a solution, it's important to ask, is the result reasonable in the context of the problem? If we had determined that Anton had run -2.5 miles, that might clue us in that we'd made some mistakes somewhere along the way, and we would need to go back and check our work. And finally, state a conclusion to the problem. So an example of a well-presented conclusion, Anton ran 7.5 miles on the treadmill. And here's kind of a lousy conclusion. Distance is 7.5. It just doesn't convey enough information. So, first step, understand the problem. Clearly define a variable to represent the unknown quantity. Write an equation to model the problem. Solve the equation and check the solution in the context of the problem. State a conclusion to the problem. So armed with these problem-solving steps, let's look at one last application. Julie is retiling the bathrooms in an apartment building. The elevator in the building has a maximum capacity of 1,400 pounds. Each box of tiles weighs 32 pounds. Julie herself weighs 160 pounds in work clothes and boots. What is the maximum number of full boxes of tiles she can transport in one elevator trip? So we want to start by understanding the problem. The idea of a maximum capacity kind of leads us to think we might be dealing with an inequality here. we want the weight of stuff in the elevator to be less than or perhaps equal to 1,400 pounds. So I'm thinking that this is going to be a problem involving an inequality. So what I have on this next screen is just some of the pertinent information we're going to need. The elevator has a 1,400 pound capacity. Each box of tiles weighs 32 pounds and Julie herself weighs 160 pounds. So we want to know what is the maximum number of full boxes of tiles Julie can transport. So what I'm going to do here is I'm going to create the verbal model that I talked about in the problem-solving steps. What's going into the elevator? Well, Julie's going into the elevator, so I need to consider Julie's weight, and we're measuring Julie's weight in pounds. And I'm going to add to that the weight of the tiles. Well, the weight of the tiles depends on how many boxes of tiles are being loaded into the elevator. So I'm going to need to consider the weight per box, and I need to multiply that number by the number of boxes. This will be the total weight going into the elevator. And this has to be less than or equal to the elevator capacity, which is also measured in pounds. So if we look at the units here, we also see that we have a reasonable model. When we multiply the pounds per box times the number of boxes, we just get a measurement in pounds. So pounds plus pounds is less than or equal to pounds. The units confirm I probably have a pretty reasonable model to work with here. Now you also might ask, why is everything in words here? Well, these words can be generalized. It might be someone other than Julie getting into the elevator, or someone might be carrying boxes of tiles which are heavier than the boxes of tiles in this problem. This is a general model that will work for a variety of different problems of this type. So now that we understand the problem, let's define our variable. So the question is, how many full boxes of tiles can Julie transport? So I'm going to let n represent the number of full boxes of tiles. And now I'm going to write an inequality to model the problem. Well, we have everything we need from the verbal model. We're going to take Julie's weight and add the weight of the tiles, which is 32 pounds per box times the number of boxes. And that needs to be less than or equal to the elevator capacity, which is 1,400 pounds. I've got my inequality. I'm ready to go. So let's solve the inequality and check the solution in the context of the problem. So to solve the inequality, I'm going to start by isolating the variable term. So subtracting 160 from both sides of the inequality, I have 32n is less than or equal to 1,240. Dividing both sides of the inequality by 32. 32 is a positive number, so the sense of the inequality remains the same. So I have n is less than or equal to some mystery number I want to calculate. So 1,240 divided by 32 equals 38.75. So I have my proposed solution. So now we want to check our proposed solution. What I have here is a graph of our proposed solution. The endpoint is the 38.75, and n equals 38 falls into our proposed solution, but n equals 39 does not. So I'm going to start by checking n equals 38, because the question is, how many full boxes of tiles can Julie transport? So if n equals 38 full boxes of tiles, then the weight going into the elevator is 160 plus 32 times 38. And pulling out my calculator, 160 plus 32 times 38, that equals 1,376. So clearly, n equals 38 is in my proposed solution set. So now let's think about what would happen if n equaled 39, or Julie tried to carry 39 boxes into the elevator. Well, one more box would weigh 32 more pounds. If I add 32 pounds to 1,376 pounds, I'm going to exceed the 1,400 pound capacity of the elevator. So the most number of full boxes Julie can transport in the elevator is going to be 38. So let's state a conclusion to the problem. Julie can transport at most 38 full boxes of tiles in one elevator trip. So to summarize, let's just go through those problem-solving steps one more time. Our first thing we need to do is really try to understand the problem. Clearly define a variable to represent the unknown quantity, then write an equation or inequality to model the problem, solve the equation or inequality and check the solution in the context of the problem, and finally state a conclusion to the problem. Before I finish, I do want to say that this has just been an introduction. Over the next several lessons, we'll be looking at many different types of applications and really looking closely at how to generate these equations. It is hard work, but we'll have several lessons over which to practice it.